In this video, we're going to look at the approaches we take to balance complex chemical equations containing molecules. We follow up in the next video with examples of balancing complex equations involving ions and polyatomic ions. The specific example we will consider in this video is the chemical equation representing the reaction between dimethylhydrazine and dinitrogen tetroxide to produce elemental nitrogen, water, and carbon dioxide. This chemical reaction was actually the reaction used to provide the energy to lift the moon lander from the moon's surface during the Apollo 11 mission. The chemical equation as it stands is currently unbalanced. We can see that on the left-hand side we have a carbon atom inside the brackets and there is a 2 outside the brackets, indicating that there are 2 carbon atoms in total on the left-hand side of the equation. And at the moment we only have 1 carbon atom on the right-hand side of the equation. We have a total of 8 hydrogen atoms on the left-hand side. There are 3 inside the brackets, and the 2 outside the brackets indicate that there are 6 hydrogen atoms associated with the CH3 group, and then the additional 2 hydrogen atoms written last in this molecule brings the total to 8 hydrogen atoms on the left-hand side. And at the moment, we only have 2 hydrogen atoms on the right-hand side. We have a total of 4 nitrogen atoms on the left-hand side, and only 2 nitrogen atoms on the right-hand side, and 4 oxygen atoms on the left-hand side, and a total of 3 oxygen atoms on the right-hand side. So this equation is clearly unbalanced at this point in time. Recalling our hints for balancing chemical equations from the previous video, we will go through a systematic approach to help us, starting with identifying any elements in the equation, because we should leave those atoms to last in terms of getting equal numbers on both sides of the equation. And we can see that nitrogen, N2, is an element. It only has one type of atom in its molecular structure, and so we will leave the balancing of nitrogen atoms until last. Next, we identify atoms that appear more than once on either side of the equation, and we're going to balance them towards the end as well. We can see that nitrogen appears more than once on the left-hand side of the equation. It appears in 2 substances, and so that is another reason to leave oxygen till last when balancing this particular equation. And we can also see that oxygen appears in 2 substances on the right-hand side, so we will leave the balancing of oxygen atoms till near the end as well. Next, we identify any hydrogen atoms and oxygen atoms, and we leave them till later as well. And this is particularly the case if water, H2O, is involved in the chemical equation, since we will find it relatively easy to balance hydrogen and oxygen atoms by adding, or in some cases subtracting, water molecules. So in this example, it means we will balance the hydrogen atoms second, and we will balance the carbon atoms first, because these are the only other atoms left remaining. We've already noted that we have 2 carbon atoms on the left-hand side. The invisible 1 subscript for the carbon atom is multiplied by the 2 outside the brackets to give us our 2 carbon atoms on the left-hand side. And at the moment, we've only got 1 carbon atom on the right-hand side. So if we put a big 2 in front of the carbon dioxide, we now have 2 times 1 carbon atoms on the right-hand side, giving equal numbers on both sides. Next, we balance the hydrogen atoms. We have 3 times 2 hydrogen atoms associated with the CH3 group, plus the extra 2 hydrogen atoms at the end of the chemical formula, giving a total of 8 hydrogen atoms on the left-hand side. And as I said before, we only have 2 hydrogen atoms on the right-hand side at the moment. So to balance that, I'm going to put a big 4 in front of the water, and that will give me 4 times 2 hydrogen atoms, or a total of 8 hydrogen atoms on the right-hand side as well. Oxygen is the next element we balance, and at the moment we have 4 oxygen atoms on the left-hand side, and on the right-hand side we have a total of 4 oxygen atoms associated with the 4 water molecules, plus another 4 oxygen atoms associated with the 2 carbon dioxide molecules, which gives us a total of 8 oxygen atoms on the right-hand side. So to get 8 oxygen atoms on the left-hand side, I'm going to put a big 2 in front of the N2O4 formula, and that gives me my 2 times 4, which equals 8 oxygen atoms on the left-hand side, to match the 8 oxygen atoms on the right-hand side. Finally, that leaves us with the nitrogen atoms, which we left till last. If we count up all the nitrogen atoms on the left-hand side, we have 2 in the dimethylhydrazine molecule, and we have another 2 times 2, which equals 4 nitrogen atoms associated with the dinitrogen tetroxide. So we have a total of 6 nitrogen atoms on the left-hand side. At the moment, I've only got 2 nitrogen atoms on the right-hand side. So we are going to put a big 3 in front of the N2 to get my 3 times 2, which equals 6 nitrogen atoms on the right-hand side, matching the 6 nitrogen atoms on the left-hand side. So this equation is now balanced, but it's always good to do a final check. We've got 2 carbons on the left-hand side and 2 carbons on the right-hand side. We've got 8 hydrogens on the left-hand side and a total of 8 hydrogens on the right-hand side. We've got 8 oxygens on the left-hand side and a total of 4 plus 4, 8 oxygens on the right-hand side. And finally, we have 2 plus 4, which is 6 nitrogen atoms on the left-hand side and 6 nitrogen atoms on the right-hand side. This equation is balanced, and we used a systematic approach to do it. And this is about as difficult as these examples get for balancing equations containing just molecules. In the next video, we will look at balancing complex chemical equations involving polyatomic ions.